Hello my dear students. In the last lecture we were discussing on the four quadrant operation of an electric drive, and we have illustrated this particular figure, and there was a loaded cage and a counterweight which was in a pulley arrangement, and all the four quadrants of operation we have understood, and all the sign conventions of the speed, the motor torque, the load torque and the power, they have been computed. So let us recap once more. The first quadrant was known as forward motoring, the second quadrant is forward braking, the third quadrant is reverse motoring, and the fourth quadrant is reverse braking. So let us explain the first four quadrants of operation. So the motor is driving a hoist. A hoist is a pulley-like arrangement. So if this is the wheel of the pulley, in one side there is a counterweight, and in the other part there is a pan-like arrangement, and there may be some load in the pan. So the motor is driving a hoist consisting of a cage with or without load, a rope wound on the drum to the hoist, this is the drum basically, and a cage, a balance weight which is known as CW or the counterweight. This is the pan, and this is the drum. So the motor is driving a hoist consisting of a cage with or without a load and a rope wound on to a drum to hoist the cage, and a balance weight of magnitude greater than that of the empty cage. Now this is very important. The counterweight has a greater amount of weight than the empty cage. So the assumption is weight of the CW or the counterweight is greater than weight of the cage. But the weight of the counterweight is less than the weight of the loaded cage. So during the throughout the analysis you have to remember this assumption. So this will be your assumption. So the weight of the empty cage is greater than the weight of the counterweight, which is greater than the weight of the cage, that is the empty cage. So this assumption you have to keep in mind. And the arrow in the figures indicates the actual directions of the motor torque, the load torque and the motion in all the four quadrants. The load torque of the hoisting mechanism is of active type. It is an active load, it is not a passive load, and it is assumed to be of constant due to negligible friction. And windage for the low speed hoist. So negligible friction and windage, this is an assumption again. So that is an assumption we are making for low speed hoist. Since the speed is very low, obviously the friction and the windage losses, they will be negligible. The speed torque curve of the hoist is represented by a vertical line passing through the two quadrants. The loaded hoist characteristics in the first and the fourth quadrant are unloaded. The loaded hoist characteristics in the first, the fourth quadrant, and unloaded in the second and third quadrant. So loading is done in the first and fourth, loaded, where in the second and third they are empty. This is also one observation you have to keep in mind. So in the first and the fourth quadrant the pan is loaded, and in the second and third quadrant it is empty. So the speed torque curve of the hoist is represented by a vertical line passing through the two quadrants. the loaded hoist characteristics in the first and fourth quadrant and the unloaded in the second and third quadrants. In the first quadrant, the load torque acts in the opposite direction to that of the rotation, and hence to the drive of the loaded hoist up, and the motor develops torque that must be in the direction of the rotation and must be positive. So let us go to the first quadrant of operation. So in the first quadrant, you can see that the load torque is in the clockwise direction because the loaded cage is heavier than the counterweight, so the force will be downwards. So here the force will be downwards because the loaded cage has a greater weight than the counterweight. So that's why the loaded cage has the tendency to move downwards. Now what will be the direction of the motor torque? The direction of the motor torque will be opposite to the downward force of the loaded cage. So if the load torque, that means the tau L is the load torque. So if the load torque is acting in the clockwise direction, the motor torque will act in the counter or anti-clockwise direction. And obviously, in order to move the cage up, the motor torque, that is tau m, should be greater than tau L. Only then the cage will move upwards. And what will be the direction of the rotation? Obviously, since the loaded cage is moving upwards, it will be in the anti-clockwise or counterclockwise direction. So the power will also be positive. So this quadrant is known as forward motoring quadrant. So these quadrants, these names you have to remember. It is known as forward motoring quadrant because you see the power will be positive. Why the power will be positive? Because omega, that is in the counterclockwise direction, that is positive, and the motor torque, it is also in the counterclockwise direction, it is also positive. So what is power? Power is equal to tau omega. So if tau is positive and omega is positive, so the power will also be positive. So now let us come to the second quadrant operation. Now the hoisting up of the unloaded cage is represented in the second quadrant. So now the load has been moved upwards and now the cage is unloaded. So as the counterweight is heavier than the empty cage, the speed at which the hoist moves upwards may reach a very high value. So obviously this is the case, because you see, as soon as you are taking off the weight, what will happen? The counterweight will try to pull up the pan in the anti-clockwise direction, so the system will be unstable. So to avoid this, the motor torque must act in the opposite direction of rotation, or the motor torque must be negative. That means the motor torque, which was positive in the first quadrant, now becomes negative, because the motor torque initially it was in the anti-clockwise direction or counterclockwise direction. Now it has to change its direction and it has to become in the clockwise direction. So the torque becomes negative. It was in the first quadrant, it was positive, it was represented in the positive x-axis. Now it will shift to the negative x-axis. So the torque becomes negative. But what about the speed? Now as there is an opposing force, what will happen? The speed will become lowered and the motor will brake, the cage will brake. That's why it is known as forward braking quadrant. It is known as a forward braking quadrant. but the speed is positive because it is not changing its direction, but it is becoming lower. So in the second quadrant, the pan is said to be slowing down. That is what we mean by braking. When a car which is traveling in the road, when you push the brakes, what happens? It slows down. What is the direction of the rotation of the wheels? It remains same during acceleration, but during braking it is also same. So similar case is occurring over here. The direction of rotation was same in the first quadrant, and the same direction of rotation is followed up in the second quadrant also. So let us view the figure once more. So we were here. So you see that the motor torque, which was in the anti-clockwise direction in the first quadrant, now becomes clockwise in the second quadrant. What about the load torque? The load torque was clockwise in the first quadrant. Now it is anti-clockwise in the second quadrant. Why? Because you see the cage is empty and the counterweight is more than the empty cage. So obviously the counterweight will try to move downwards and the cage will try to move upwards. So if the motor torque does not change, the direction of the motor torque does not change, what will happen? This tau L and tau M will add up, resulting in a very huge speed, and what will happen? This empty cage will just fly over the counterweight and the system will become unstable. So what happens? It happens over here. You can see the tau M becomes negative, but omega becomes positive, but its value becomes low. So what will happen to the power? It is wrongly written over here. It will be negative. The power becomes negative because omega is positive, tau M is negative. So the power will become negative. Now let us come to the third quadrant of operation. So in the third quadrant represents the downward motion of the empty cage. So the third quadrant represents the downward motion of the empty cage. So what happens? It has moved upwards. It has done its job. The weight has been unloaded and the motor has slowed down and it has stopped. Now what will happen? Now the cage has to be moved downwards for again loading. So for that purpose, what will happen? What will happen? The motor torque will have to, the speed has to change its direction, but the motor torque will remain in the anti-clockwise direction. So the downward journey will be opposed by a torque due to counterweight and the friction and the transmitting parts. So to move the cage downwards, the motor torque must be in the direction of rotation. So what will happen? So this will be the load torque and this will be the motor torque, same as the second quadrant, but what will be the direction of the rotation? The direction of rotation will now become clockwise. So initially it was anti-clockwise, now it will become clockwise. So in this particular case, the motor torque will become negative, the speed will become negative. So what will happen? The power will be minus Tm into minus omega. So it will be tau M omega. So electric machine acts as a motor but in the reverse direction compared to the first quadrant, and that's why it is called reverse motoring. The torque is negative as the speed is increased in the negative direction, but the power is positive. We have deduced that already, and that is known as reverse motoring. So let us go to the diagram once more. So if you see the third quadrant, what about the second quadrant? So the speed was in the clockwise, in the anti-clockwise direction in the second quadrant. So now you see in the third quadrant, the speed is in the clockwise direction. but the direction of the load torque and the motor torque was same. It is in the same as that of the second quadrant. So what is happening? The motor torque, it was already negative over here. Now it is already negative. The speed was positive, but the direction of the speed has changed. Now it is negative. So minus into minus plus. So P becomes positive, and the motion is in the downward direction. So now let us take the fourth quadrant operation. So the fourth quadrant has the downward motion of the loaded cage. So as the loaded cage has more weight than that of the balanced counterweight, so to limit the speed of motion, the motor torque must have opposite polarity with respect to the direction of the rotation and acts as a brake. So what is the scenario? This is the counterweight, and this is the cage, the loaded cage. So now what will be the load torque? It should be in the downward direction. So tau L will be in the downward direction. So what will be the direction of the motor torque? The direction of the motor torque will have to reverse. So the motor torque will become positive now. So initially it was in the anti-clockwise direction and it was negative. Now it has become positive. But what about the direction of rotation? The direction of rotation is in the same direction as that of the third quadrant. In the third quadrant, the direction was in the clockwise direction, and the direction of rotation in the fourth quadrant is also in the clockwise direction, but the value of omega is reduced. So omega is reduced. So that's why it is called braking, and it is called a reverse braking. So there has to be a difference between the second quadrant braking and the fourth quadrant braking. So the second quadrant braking is called the forward braking. The fourth quadrant braking is called reverse braking. So the first quadrant operation is called forward motoring. The third quadrant operation is called reverse motoring. And obviously, if you see, the motor torque sign is positive. The sign of the motor torque is positive over here. So tau m, it is positive because it is in the counterclockwise direction, but speed, it is in the clockwise direction and it is negative. The omega is negative. So when you multiply a positive quantity with a negative quantity, what is the formula for power? Power is equal to tau omega. So it should be equal to tau m into minus omega. So it should be negative. So the motor torque sign is positive, but as the speed has negative direction, the speed has got negative direction, the power will be negative. So the quadrant is designated as the reverse braking quadrant. So now if we see the 4 quadrant operation over here, so we have completed all the quadrants starting from 1, 2, 3, 4, and you see that we have covered the entire range of torque from positive to negative, and we have covered the entire range of speed from positive to negative in all the 4 quadrants. So that's why an electric drive is called flexible. So you can exploit all the directions of rotations, all the combinations of torque and speeds, whether it is positive, whether it is negative, its range, you can exploit everything at your will. So that's why electric drive is advantageous in this regard, as we are studying advantages in the last to last lecture. So we have seen that it is flexible. Why flexible? This is the reason why it is flexible. So we will stop over here for today. Thank you.